Christoffel symbols are what? Are just how your frame, when these e's cover the tangent space, we call it a frame. How your frame differentiate with respect to each other. How elements in the frame differentiate with respect to each other. The result, we call it Christoffel symbols. And so each I, J, and K, they run from 1 to n. We can lump them in matrices, matrix form. So these are n matrices, right? Actually, they are square matrices, right? Because I and J run from 1 to n. They are n by n. So they are n cube elements. If you give me your gammas, which is how each unit vector differentiates with respect to the other, go and do it the very hard way, whatever. Alternatively, we will see a much easier way to get the gammas next lecture, hopefully, maybe today. I don't think so. We'll see. So, like I said, by linearity, if you know how these gammas, if you get these gammas, now I can extend any x in terms of the e's, any y in terms of the e's, and by linearity, I can get the nabla x, y for any x and y. Here is the ek component, which, like I said, this is the partial xk or qk, the kth component. This is x acting on the kth component of y, plus gamma ijk xi yj, just by linearity. This is in our language, this is the lead derivative along x of yk, or if you want to write it a way common to engineers, it's partial yk, partial xi times xi. And I have summations over all indices. Also this, if you want to write it the way we like to do it in engineering, this is x as a row, gamma k as a matrix, y as a column. A row, matrix, column, the result is just a number, a scalar. This is the scalar that is the coefficient of in the k direction, in addition to this guy. Okay? So, so this is actually partial y, partial q's in the x direction that doesn't transform well under change of coordinates, plus the gamma ij. So this gives you a vector, right? Plus here is the vector that makes things transform well under change of coordinates. The kth entry of it is this guy. Okay? So whenever you need to do the derivative, it's two terms. The first is just the usual one. Plus, here is the correction that comes from the Christoffel symbols, which has to do with the derivative of each unit vector with respect to the other, which means it's related to the curvature of the vector. Okay? We'll see how to determine them later, but we know at least a hard way of determining them. Okay? Any questions so far? I know it's a bit abstract to us as engineers, but you can be much more abstract than that. Any questions so far? Any question about?
So this thing lives in the tangent space, right?
The result lives in the tangent space.
Yeah, but what about both separately?
No. Yeah, that's a very good question. This guy doesn't live in the tangent space, neither this guy. That's a very good question. But together, which is interesting, together they both live in the tangent space. Okay? So now I can define the derivative along the curve. I will use this definition. So now I can say, what is the derivative? This was my aim at the very beginning. Derivative of a vector y along the curve. Right? This was my thing. Well, your animal that you just created needs two vectors. So you're talking about nabla y along the vector here, then the natural vector that is in the direction of your curve is the velocity, right? And because of the construction of this guy, it really doesn't need here a vector field, right? Any vector will suffice. So the velocity vector of the curve is not a vector field, it's not defined everywhere, it's just defined on the curve. That's fine. So the curve is gamma, so in coordinates is q1 up to qn, and gamma prime is q dots. So I will use this exact definition. I'll use this exact definition, replacing all the x's with q dots, okay? The same definition, so nabla y along the gamma prime, the derivative of y along the curve is, the first thing here is partial y, okay, partial, I'm replacing x's with q dots, so this is qi dot, I'm sorry, this is actually q, right? We differentiate with respect to the coordinates. Now the vector field x, I'm replacing it with qi dots. Plus gamma I j k, xi is qi dot yj. So this is the derivative of a vector along the curve, okay? I will say this invokes actually to say, what do we mean by y is parallel? This is a definition for parallel along gamma. Well, it means that that y doesn't change along gamma, right? So a vector field y is called parallel along the curve if it doesn't change along the curve, right? And this actually suggests also that, remember when we have a vector field, when you have a vector, just a vector in the tangent space, just a vector, 1 and 0, we didn't have a unique extension, right? Everybody can extend it the way he or she likes. So now I can uniquely extend this guy. So if I have given this guy and the gamma, say gamma of 0 is p, there exists a unique extension vector field y of v along gamma, and this is called the parallel transport of v along gamma. I have just a vector. So this is your curve gamma, and I have just a vector v. Just a vector, 1 and 0. And by this vector I want to construct a vector field defined not necessarily everywhere, but at least on the gamma. How can I extend this guy in a unique way so we don't have different answers? Well, that's fine. I can extend it by a vector such that they are parallel to itself along gamma. So y, obviously, to be parallel along gamma, y satisfies this guy. Which means, let's get this guy here, please. And if you see here the very first thing, partial y, partial q times q dot, this is chain rule of yk dot, right? Plus gamma ijk qi dot of t yj, this is of q of t, and this should be 0, with y of time 0 was the vector v. What type of equation is this? What type of equation is this?
Equation of motion. Yes. Y is a vector.
Y is a vector. This is simply an ODE in y, right? It's just an ODE in y. This guy is a function of time. They are given from the curve. This is now the function of q's, but q is a function of time. So this is a function of time, function of time. So y dot is a function of u, right? This is a differential equation. Y dot is a function of y, I'm sorry. So this is a differential equation, and you have an initial condition, right? Your initial vector. So I can indeed create y vector along this guy. They are all parallel in gamma. In what sense? Parallel in this sense, that it doesn't change along gamma. Okay, anyway, this was aside. The point, these 2 points, the parallel along gamma and parallel transport, the concept of parallel transport, they are on a side. But the great thing that we got so far is this blue equation, is that I can differentiate a vector along a curve because there was something that is waiting for us so far. What was that? The acceleration of the curve. I want from the beginning of the lecture to define the acceleration of a curve, right? And this necessitates to differentiate along the curve. Here is the derivative along the curve. So please now replace all y's. This is the derivative of y. I need the acceleration. The acceleration is the derivative of the velocity of the curve. So I'm going to replace all the y's with q dots. And that's it, okay? So the acceleration from the blue equation, the acceleration of a curve gamma is the derivative of the velocity, right? Acceleration derivative of velocity, gamma prime, along the curve. Now I can do it. So in the equation above, just replace each y by q dot. So you have nabla gamma prime is gamma prime. This is the acceleration, which sometimes we denote as geometric acceleration. It's the total acceleration.